Hello, we're going to talk about the limits of trigonometric function. To calculate the limits of trigonometric function, there are some theorems which help us in calculating those limits. Theorem number 1 is from the definition of the limit. The limit as x tends to a, sin x is tending to sin a. You replace x by a. From the definition of the limit, we know that as a variable tends to a number, then the function is tending to what? That is to say, from this property number 1, our variable is x and the number is a, which means as x tends to a, our function, which is sine x, is tending to be what? Our sine x is tending to be sine a if x is tending to be a. Property number 2, limit as x tends to a of cos x. As x is approaching a, then cos of x is tending to be what? Cos of x is tending to be cos x. This cos of x here is tending to be cos of a, as x is tending to be our a. That is to say that you replace x by a. When we take an example, as x here tends to pi over 2, we need to know as x is tending to pi over 2, then this sine x is tending to what? So you see here on this step on solution, as x tends to pi, sine x will be equal to sine pi over 2, and sine pi over 2 is 1. Example number 2, limit as x approaches pi over 3, cos of x will tend to what? As x is tending to pi over 3, our cos of x will tend to be cos of pi over 3, which is equal to a half. It means that as x is tending to pi over 3, our function, which is cos x, is tending to be a half. Property number 3, limit as x tends to a of tan x is equal to tan a, but a should be different from pi over 2 plus k pi, where k is an integer. Here they want to mean that a should be another angle which is different from pi over 2 and other angles which are in the same quadrant with pi over 2, because the tan of pi over 2 will give us a mass error. Property number 4, we need to know now the nature of tan x, as x is tending to be a, and a is equal to pi over 2 all other angles in the same quadrant with pi over 2, which is pi over 2 plus k pi. Here we'll study the nature of our limit. That is to say, we're going to see on the right hand side and on the left hand side. As x tends to a from the left hand side, our tan of x is tending to be a positive infinity, where a is pi over 2 or pi over 2 plus k pi. And as x tends to a from the right hand side, our tan of x is tending to be negative infinity, as a is equal to pi over 2 or pi over 2 plus k pi. These two properties, property number 3 and property number 4, they are different. Here we are using, on property number 3, we are using an angle which is not within this range of pi over 2 plus k pi, but here on property number 4 we are using an angle which is in the range of a is equal to pi over 2 or a is equal to pi over 2 plus k pi. When we take an example, as limit x tends to pi over 4 of tan x, here you need to know the nature of tan x as x is tending to be pi of 4. So when you replace x by pi over 4, our tan x will tend to be 1 as x is tending to be pi over 4. Limit as x tends to pi over 4, our tan x will tend to be square root 3 as x is tending to be pi over 3. This example A and example B, they are satisfying the property number 3 because pi over 3 and pi over 4, they are not equal to pi over 2. But when we take an example of part C, where x is tending to pi over 4, and you need to know the nature of our tan x. When you replace x by pi over 2, it will be tan pi over 2, which is equal to infinity. And you need to know the nature of this infinity. Then when you study the sign of this mass error, because when you study the sign of tan pi over 2, it will be a math error. This will give us, you state the right and the left hand side limit. As x is tending to pi over 2 from the right hand side, our tan x is equal to negative infinity. Limit as x tends to pi over 2 from the left, our tan x will be tending to positive infinity. Property number 5 is the limit as x tends to a of cotan x. We need to know the nature of cotan x as x tends to a. So it will be cotan a, but as a is different from k pi, where k belongs to the set of integers. But when when a is equal to k pi, maybe take an example of a is equal to pi when k is 1. When you find the cotan of pi, it will be a math error. That is to say, you're going to find the nature of the infinity. You study the sign of the left hand side and the right hand side. As x tends to a from the right hand side, the cotan of x will be tending to be positive infinity. That is in case when a is equal to k pi, where k is an integer. Remember that when you replace k by any number, a will be different depending on the value of k. But when you find the tan and the cotan of those different angles, they are going to give you the same value. So a limit as x tends to a from the left hand side, this cotan x will tend to negative infinity, but as x is equivalent to k pi, where k is an integer. So that is the property of cotan, it is almost the same as the property of tan, but for the domain of definition, here they are excluding k pi, but on tan they are excluding pi over 2. Property number 6, we want to prove limit as x tends to 0 of sin x over x equal to 1. Once we are going to prove on the right and on the left hand side limit. When we start with the right hand side limit, as x tends to 0 as from right, our sin x over x is tending to be 1. Here we have the value of x. Here we have the value of sin x over x. When you replace x by 1, it will be sin 1 over 1 that gives us it will give us 0.84. When x is 0.9, our sin 0.9 over 0.9, it will give us 0.87. When x is 0.8, our sin of 0.8 over 0.8 will be 0.897. As x continues to reduce, you see here 0.5, 0. something, up to 0.1, then sin x over x, you see how it also gives different values, 0.985. You see how they are changing up to this one. What can you conclude on this? You see, as x is tending to be 0, then sin x over x is tending to be 1. You see on this part here, on this side here, we have 0.999, which is approximately to 1. On the right here, this is 0.00001, which means on this side here, our x is tending to be 0, but on this, our sin x over x is tending to be 1. That's why they say that limit as x tends to 0 from the right hand side of sin x is equal to 1. When you also prove that using the same concept on the left hand side, you can observe clearly here -1, -0.9, -0.4, -0. something up to these values. You see they are reducing negative here up to -0.001. But when you replace these values of x in our function sin x over x, you see the nature of the values you're getting of sin x over x. You replace there. Remember, x is in radians. When you use your calculators, which are in degrees, you will not get these values. In conclusion, therefore, the limit as x tends to 0, sin x over x is tending to be 1. In other words, we have other properties that we'll be using in finding the limits of our trigonometric function. Limit as x tends to 0 of x over sin x is also 1. Limit as x tends to 0 of sine of ax over bx, it will be a over b. Limit as x tends to 0 of ax over sine bx, it will be a over b. Limit as x tends to 0 of sine ax over sine bx, it will be a over b. Limit as x tends to 0 of x over tan x will be 1. Limit as x tends to 0 of tan ax over bx will be a over b, and limit as x tends to 0 of ax over tan bx will also be a over b. You see, it's a over b, a over b. It depends on which identity you want to use. But if you want, this property here, E, can also be proved by using the table that we have talked above. You draw the row of x and another one of tan x. You assume the values you see as x is approaching to be 0, then this x over tan x will be tending to be what? You can put those values, 1 of x, they are approaching 0, and you want to see the nature of x over tan x will be approaching to be what? Examples. Evaluate the limit as x tends to 0 of sine 5x minus sine 3x over sine x. Solution. X tends to 0, sine 5x minus sine 3x over sine x will be sine of 5 times 0 because x is tending to 0 minus sine of 3 times 0 over sine 0, which is giving us 0 over 0 indeterminate form. Now we need to remove this indeterminate form. But we remember that when we have the two terms which you can't add them, divisible by a denominator, we can split it into two terms of the same denominator as sine 5x over sine x minus sine 3x over sine x. When you add these two terms, they are giving you sine 5x minus sine 3x over sine x because these two terms, they have common denominator. But when you remember about the properties of the limit, there is a property which says that the limit of the difference is the difference of the limit, which means if x, the limit as x tends to a of sine 5x over sine x minus sine 3x over sine x is the same as the limit as x tends to 0 of sine 5x over sine x minus limit as x tends to 0 of sine 3x over sine x. But from this property which says that limit as x tends to 0, then sine ax over sine bx will be equal to a over b. When we refer it to our limit here, this limit, it will be limit of sine 5x over sine x minus limit of sine 3x over sine x as x tends to 0. But this one here of sine 5x, this one of sine 5x as x tends to 0, it will give us 5 over 1. And this one here of sine 3x over sine x will also give us 3 over 1. Then it will be 5 over 1 minus 3 over 1, which will give us 2. Therefore, the sine of 5x minus sine of 3x over sine x will be equal to 2. Example B. Evaluate the limit of cos of 3x minus cos x over x squared. When you replace there 0, it will give us infinity over infinity, which is in indeterminate form. But when you observe on the numerator cos of 3x minus cos of x, we can write it as one term by using the factor formula. Cos of 3x minus cos x is the same as negative 2 sine of 3x minus x over 2 sine 3x plus x over 2, which is equal to negative sine x sine 2x. This factor formula is from cos of p minus cos of q. Remember that property from the compound angle formulas and factor formula. Cos of p minus cos of q is the same as negative 2 sine p minus q over 2 sine p plus q over 2. So when you, instead of writing cos of 3x minus cos x, we can write a negative sine 3x sine 2x. Then our limit will be limit as x tends to a of negative 2 sine x sine 2x over x squared. Then, but x squared is the same as x times x, and this is the product here. It can be negative 2 sine x over x times sine 2x over x, which is the same as negative sine x sine 2x over x squared. But we remember also from the properties of the limit that the limit of the product is the same as the product of the limit. That's why here you see that we are finding the limit of each factor, because that you can multiply two functions, then after getting the product of those two functions, you find the limit of the product. But you can also find the limit of each function, then after you multiply the answer you have got. So it will be negative 2 sine x over x as x tends to 0, and limit as x tends to 0 of sine 2x over x. But by using the above properties that we have talked about, limit as x tends to 0 of sine x over x is 1, and limit of 2 sine x over x as x tends to 0, it will be 2. Therefore, when you replace there, our limit as x tends to 0 of cos 3x minus cos x over x squared will be equal to negative 4. We have the exercise here. Try these numbers, evaluate the following limits from a to e, but remember to apply the properties that we have talked about, and where x is not approaching 0, like example e, and when you substitute there you find 0 over 0, you have to try by all means to transform it into the identities we have.